Virtualization on the cloud. About this module. Module 1. Virtualization. Introduction. In this module, you'll learn about virtualization and the benefits it provides in a cloud environment. You'll discover that businesses use virtual machines to improve the efficiency, scalability, and flexibility of their IT resources. You'll explore how virtual storage reduces the physical storage that users need on their devices. And you'll learn how engineers use virtual networks to isolate networks for development purposes and connect separate networks together. Learning objectives. After completing this module, you should be able to describe the purpose and benefits of virtualization. Explain the function and features of virtual machines. Explain the function and features of virtual storage. Explain the function and features of virtual networks. The power of virtualization. Virtualization is the process of creating a virtual representation of a physical resource, such as a server, a storage device, or a network. Virtualization in a cloud environment offers a lot of benefits to users. It enables multiple virtual computers to run on the same physical host computer, each with its own operating system, OS, and applications. It can improve the efficiency, scalability, and flexibility of information technology, IT, resources, as well as reduce costs and environmental impact. It enables cloud customers to access services over the internet, without having to manage or maintain the underlying physical infrastructure. It also enables cloud customers to scale up or down their resources on demand, depending on their needs and requirements. Cloud providers offer three key types of virtualization: virtual machines, virtual storage, virtual networks. The following illustration shows people interacting with a screen displaying statistical charts. A virtual machine generates the chart by accessing data in virtual storage via a virtual network. All of these virtual items are hosted in the IBM cloud. Let's explore each of these virtualizations in more depth. Virtual machines. When IBM released their Model 5150 model of their PC line in the early 1980s, personal computing became mainstream. People could affordably buy their own computer to create documents and spreadsheets, and play games. As the personal computer revolution became a part of culture, people wanted to do more and more with computers, such as try different operating systems and explore new software. To install a new operating system on an early computer, a user had to first erase everything on the hard disk, including all their data. If they later wanted to go back to the old operating system, they again had to delete all their data and then reinstall the original operating system. More than one computer. When you get a new cell phone, you'll spend time logging into your accounts, setting up your important apps, and transferring your contacts. Imagine now that you start a new job and you're given a company phone too. You must go through the entire process of setting up the second phone with all your business accounts, apps, and contacts. You're only allowed to use the company cell phone for business-related tasks, so you keep your personal phone for your own tasks. What if you had to do this for every area of your life? You'd have to set up and use a phone for your basketball league, another for your book club, and so on. This is repetitive, expensive, and takes up a lot of space in your bag. Like the cell phone example, a company might have a dedicated computer to perform a particular business function, such as running nightly processes for inventory counts. Inventory counts are complex business processes that track goods in and out of warehouses and ensure optimized levels of inventory. This nightly process requires data from multiple sources including sales data, purchase orders, and shipment information. These types of computers often require complex setups, such as needing high processing power, large memory capacity, and specialized software applications, to perform their task. So each task required a dedicated computer that was specifically set up to manage that task and that users could not change. To solve this challenge, individuals and businesses would buy one personal computer, workstation, or server for each task. This very quickly became expensive, much like buying multiple cell phones for different activities in your life. Plus, in addition to the cost of the hardware, the machines used power and space, and required ongoing maintenance. What is a virtual machine? The situation changed with the development of virtual machines. A virtual machine, VM, is a software-based emulation of a physical computer that can run different operating systems and applications. Virtual machines run on a physical computer, and each physical computer can run, or host, multiple VMs. Have their own virtual hardware, such as a CPU, memory, disk, and network devices, that are isolated from the host system and other VMs. Users can easily create, copy, move, or delete a VM without affecting the physical hardware. By using VMs, companies can start their dedicated VM to run the nightly process, and then when the process ends, shut the VM down until the next evening. This releases resources for another VM to use during the day. The concept of virtual machines dates back to the 1960s. IBM developed systems that allowed different users to run different operating systems on a single mainframe computer. These systems were based on the idea of virtualization. Virtual machines continued to improve over the next few decades. In the 1990s and 2000s, they became more popular and widely used with the emergence of platforms such as VMware, Microsoft Virtual PC, Xen, KVM, and Hyper-V. Originally, virtual machines were primarily used in business scenarios. But today, the technology is also being regularly used in the cloud. Testing and development. VMs allow developers and testers to create multiple software and hardware environments. They can use different operating systems and software configurations without using multiple physical machines. They can use VMs to simulate different network conditions and user behaviors. And they can also use them to develop software that needs access to low-level resources or devices. Low-level resources and devices are the computer's basic components. Server consolidation. VMs enable multiple servers to run on a single physical machine. This reduces hardware costs, power consumption, and space requirements. They can also improve server utilization and performance by dynamically allocating resources according to the workload demand. Disaster recovery and backup. Engineers can replicate VMs and migrate them across different locations. This provides high availability and fault tolerance. They can also easily back them up and restore them, ensuring data protection and recovery. Security and isolation. VMs provide a layer of abstraction between the guest operating system and the host system. This prevents malware or malicious users from accessing or compromising the host system or other VMs. Engineers also use VMs to create sandboxed environments for running risky applications. A sandboxed environment is an isolated VM that can run code from unknown or untrusted sources without impacting other applications or computers. How do virtual machines work? Imagine you own a catering company that provides different meals and desserts for large events. Your company owns a kitchen with many specialized appliances, such as blenders, mixers, and a pizza oven. However, the cost of the appliances and of the kitchen space is expensive, and your company is not always using the space. Also, sometimes you only need to use a few of the specialized appliances, and the rest of the appliances will just sit there unused, taking up space. Now, imagine that you could rent out your kitchen space and appliances, so that many catering companies can share the use of them. Overhead view of many people working in a busy kitchen. Image source, photo by Drew Gilliam, opens in a new tab, on Unsplash, opens in a new tab. Virtual machines work similarly to a shared kitchen. In a shared kitchen, multiple people can use the same appliances and space. Similarly, using virtual machines, multiple operating systems can share the same physical resources, such as CPU, memory, and storage, while maintaining isolation and independence. Users can install their own operating systems, applications, and software configurations to suit their specific requirements. Just like how different catering companies can bring in their own required ingredients to prepare a meal. Virtual storage. Computers work by processing digital data. Whether that data is in the form of a spreadsheet or a streaming movie, the main function of a computer is to store, send, and retrieve, and process large amounts of ones and zeros. Individuals and companies transmit data around the internet every day. But when it's not in use, it needs to be stored somewhere. In traditional computing, users would store data on a disk drive that was a part of their personal or work computer. But today, storage is virtual. This virtual storage refers to the pooling of physical storage from multiple network devices into what appears to the user as a single storage device. Users can manage their virtual storage from a central console. Dropbox, Box, and Google Drive are examples of virtual storage that businesses and consumers commonly use. Today, people park their cars in a garage, driveway, or in a space on the street. If they live in a big city, they might know how difficult it can be to find a parking space if they don't have a dedicated space. The challenge is that there's not enough physical space available. In a future with self-driving cars, the problem of finding parking might disappear. Cities could pool their parking resources so any car can use any of the available parking spots in the city. A car would simply drop someone off at their home and then drive itself to an available parking space. People are no longer constrained by the available parking spaces near where they need to be. Similarly, virtual storage is a way to store data from a device and retrieve it back over a network or the internet. Virtual storage enables devices connected to the network to store and access large amounts of data virtually, without needing large amounts of storage space on the device itself. Cloud providers use virtual storage to store their users' data across different storage devices on the cloud. How does virtual storage work? Virtual storage uses remote servers to store data, such as files, business information, videos, and images. But how do users interact with that data? Let's walk through an example of this process. Numbered divider 1. Upload data. Users upload data to servers via an internet connection. The server saves the data on a virtual machine running on a physical server. Numbered divider 2. Manage data. To maintain availability and provide redundancy, cloud providers will often spread data across multiple virtual machines in data centers located across a region or across the world. Storing data in multiple locations has no impact on the users other than improving the availability of their data. Numbered divider 3. Increase storage space. If the user needs more storage space, the cloud provider can start more virtual machines to handle the load. Numbered divider 4. Access data. Users access data in cloud storage through an internet connection. The software they use to do this might be a web portal, a browser, or a mobile app. Virtual storage enables organizations to store, access, and maintain data so that they don't need to own and operate their own data centers. Virtual storage is scalable, allowing organizations to expand or reduce their data footprint depending on need. Virtual storage on the cloud. With the ability to store data on remote servers and access it from anywhere with an internet connection, cloud storage has become an essential tool for businesses and individuals alike. There are 4 main models of cloud storage available: public, private, hybrid, and multi-cloud. Each model offers its own unique set of benefits and is designed to meet the specific needs of different users. Public cloud storage. In the public cloud storage model, an organization stores data in a service provider's data centers. Other businesses will also utilize these data centers. Data in public cloud storage is spread across multiple regions. Cloud providers offer it on a subscription or pay-as-you-go basis. Public cloud storage is elastic. This means that users can scale their data storage up or down depending on the needs of the business. Public cloud providers typically make data available from any device such as a smartphone or web portal. Private cloud storage. In the private cloud storage model, an organization uses its own servers and data centers to store data within their own network. Alternatively, businesses can use dedicated servers and private connections from cloud service providers. These servers and connections are not shared by any other business. Businesses that require more control over their data and have stringent compliance and security requirements typically use private cloud storage. Hybrid cloud storage. The hybrid cloud storage model is a mix of private and public cloud storage models. A hybrid cloud storage model allows businesses to decide which data it wants to store in which cloud. They might store sensitive data and data that must meet strict compliance requirements in a private cloud, and store less sensitive data in the public cloud. Multi-cloud storage. In the multi-cloud storage model, an organization uses multiple public cloud providers to store different types of data. Multi-cloud storage can help businesses avoid vendor lock-in, optimize costs, improve performance, and enhance security. Virtual networks. A virtual network is a network that uses software instead of physical hardware. It behaves and operates like a regular network, but it exists only in the digital world, not in the physical world. Virtual networks use virtualization technology, which allows engineers to create a network using software-based network components. Can simulate all the functionality of a physical network, including routing, switching, firewalling, and load balancing. How do virtual networks work? Virtual networks use virtual routers, virtual switches, and virtual firewalls in the same way that physical networks use physical components. They exist in a layer between physical network components and the workloads that use them. Hardware layer. The hardware layer contains physical network components like routers and servers. These provide the foundation for the virtual network. Network virtualization layer. The network virtualization layer is a software component that creates and manages virtual networks on top of physical infrastructure. It allows multiple virtual networks to coexist and operate independently from each other, while sharing the same physical resources. Virtual network layer. The virtual network layer contains virtual routers, switches, firewalls, and other devices that provide the network services and connectivity needed by virtual machines and other network resources. This layer includes additional network services like DHCP and DNS. Application and services layer. At the top layer, there are the applications and services, or workloads, that rely on the underlying virtual network infrastructure and services to provide network connectivity. Take a moment to review the following diagram of the architecture of a virtual network. You'll notice that multiple virtual networks use the network virtualization layer to provide network connectivity to the application and services layer by connecting the hardware layer to each virtual network. Users commonly use virtual networks for various purposes, including isolating and securing different segments of a network, such as development, testing, and production environments. Connecting different physical locations or cloud services over the Internet, using encryption and tunneling protocols. Enhancing the performance and availability of network services, by distributing the workload across multiple servers or regions. Experimenting with new network configurations or technologies, without affecting the existing infrastructure or requiring additional hardware. About this module. Module 2. Containerization. Introduction. In this module, you'll learn about the ways that developers use containers to modularize development and extend hardware resources. You'll explore how containers differ from other virtualization technologies. And you'll examine some examples of the software that developers use to build and manage containers. You'll also discover the benefits of using containers in the cloud. Learning objectives. After completing this module, you should be able to describe the purpose and benefits of containers. Explain the concept of virtualization and its relevance to cloud computing. Differentiate between containers and virtualization. Identify and compare the capabilities of container tools, Docker, Kubernetes, and Podman. Describe the purpose and benefits of using containers in the cloud. Containers. Containerization is a lightweight form of virtualization that enables applications to run in isolated environments on a single host operating system. Containers are portable, easy to manage, and offer fast startup times. By using containers in cloud environments, cloud developers don't have the cost and management associated with a full physical computer or even a virtual machine. This means they can make their applications and services run faster and require less resources. What is a container? Many automobiles can do a lot of things beyond simply driving from one place to another, such as heating the interior, cooling the interior, playing music, operating in the dark, operating in the heat, operating in the cold, transporting one person, transporting more than one person, transporting cargo. Automobiles have these abilities regardless of whether a person needs them. They're an all-or-nothing type of technology. For example, suppose you need to go to the grocery store for a few items that is just a few blocks from your house on a spring day. If you use an automobile, you're using a vehicle that has features you won't use on that trip. You don't need to turn on the heat or air conditioning, you have empty seats, and you only need to transport a small amount of cargo, a grocery bag. In this case, perhaps a smaller, lightweight vehicle might be more efficient. You could jump on a bicycle or scooter that has a small basket attached, ride to the store, and get what you need. The resources of a large automobile are more than you need for this trip to the store. Using less resources means you can put the unused resources to another use or just not use them at all, saving money and wear on your car. Containers are like scooters and bicycles as computers are like cars. Like a scooter or bicycle, containers are lightweight and use only the features needed for a specific task. Containers provide many benefits compared to using physical computers. Lightweight and portable. Containers use a shared operating system and only contain the application code and dependencies. Computers have their own operating system and hardware resources. Isolated and secure. Containers run in a sandboxed environment, which limits their access to other containers and the host system. This reduces the risk of code running in a container impacting other applications or the operating system itself. By contrast, malware and other security threats can affect computers. Scalable and efficient. Developers can easily deploy, replicate, and update containers across multiple hosts. Computers require more time and effort to set up, maintain, and upgrade. Compatible and interoperable. Containers can run on any platform that supports the container software technology. By contrast, computers might have compatibility issues with different hardware or software configurations. Containers and virtualization. Containerization and virtualization are two methods of creating isolated environments for running software applications. They both aim to improve the efficiency, security, and portability of software development and deployment. However, they differ in significant ways. Virtualizing computer resources typically means creating one or more virtual machines to provide a resource for performing various tasks. Containerization means creating containers that run applications and services for performing tasks. Select each number in order on the following diagram to learn about the similarities and differences between virtual machines, VMS, and containers. Virtualization involves creating virtual machines, VMS, that emulate the complete operating system and hardware on a physical server. Containerization involves creating containers that share the same operating system and hardware as the host server. Each VM has its own operating system, applications, libraries, and configuration files. Each container has its own applications, libraries, and configuration files. Multiple VMS can run on the same physical server, each with its own resources and settings. Each container is a lightweight and self-contained package of software that can run anywhere that supports the same operating system. Virtualization enables users to run different operating systems, such as Windows and Linux, on the same physical hardware at the same time. It also enables users to isolate different applications from each other and the host. Containerization enables users to run multiple applications on the same server, each with its own dependencies and environment variables, and to isolate applications from each other. The main difference between virtualization and containerization is what parts of the underlying computing environment each uses. Virtualization uses the hardware of the host computer, but has its own operating system and software. Developers call this hardware abstraction level. Containerization uses the hardware and operating system of the host computer, but has its own software. Developers call this operating system abstraction level. In cloud computing, when developers abstract a layer, it means that they're creating a layer of separation between the container or virtual machine and the hardware or operating system that the container or virtual machine runs on. Abstraction makes complex systems easier by focusing on the essential features and ignoring the irrelevant ones. When you use your smartphone, you don't need to know how the hardware or the software works internally, you just use the apps that provide a simple and consistent interface. Containers work in a similar way. They provide a simple and consistent interface for the code to run on any operating system or hardware. In other words, they abstract the operating system. These abstraction levels determine some of the behavior and characteristics of VMS and containers. Because containers do not need to start an independent operating system, they are more efficient than VMS in terms of resource utilization, startup time, and performance. Because they share the same operating system with the host computer and each other, they are less secure than VMS. And because containers can only run on hosts that use the same operating system as themselves, they are less compatible with host software than VMS, which have their own operating system. Examples of container tools. There are many container applications in use today. Some are proprietary and others are open source. 3 widely used container applications to be familiar with are: Docker, opens in a new tab, which is the most popular tool for creating and running containers. Kubernetes, opens in a new tab, which is a system for orchestrating multiple containers across different machines or clouds. Orchestration is a way to manage and automate tasks across multiple cloud platforms. Podman, opens in a new tab, which is a newer alternative to Docker for creating and running containers that offers some advantages in security and simplicity. Docker. Docker is a tool for creating and managing containers using a client-server architecture. It has a background process called the Docker daemon that handles container operations and exposes an API for communication with other tools and services. Users can interact with the daemon using the Docker command line interface or graphical user interface tools. Docker also supports Docker Swarm, a native orchestration tool for managing multiple Docker hosts and containers. Kubernetes. Kubernetes is a tool that helps users to manage groups of servers and containers. It automates tasks like deploying and scaling containers and makes sure they are balanced and healthy. Kubernetes uses pods, which are groups of containers that share resources. Users can interact with Kubernetes using command line or graphical tools. Podman. Podman is a tool that can manage and run containers without needing an additional program to do so. It is based on a model used by Kubernetes, which allows it to run multiple containers together. Users can interact with Podman using a command line tool or graphical tools. While all 3 container tools do many of the same things, there are differences that impact how users use them in terms of security, architecture, and functionality. Security. Docker needs access to the core of the host operating system or root privileges to run its background process, which can be a security risk. Podman and Kubernetes, on the other hand, run as non-privileged users by default and don't need a background process. This makes them more secure and less vulnerable to attacks. Kubernetes also uses role-based access control to enforce security policies. Architecture. Docker bundles all its container features into a single tool. Kubernetes separates its container features into different components. Podman uses existing Linux features to run containers without needing a background process. This makes the Podman architecture more lightweight than the others. Functionality. Docker is mainly for managing containers, but can also do basic orchestration with Docker Swarm. Kubernetes is mainly for orchestrating containers, but users can also do basic container management with its command line tool kubectl. Podman is mainly for running containers, but can also do basic pod management using the podman command from the command line. Docker, Kubernetes, and Podman are different tools for different purposes. To summarize, Docker is suitable for developers who need a simple and comprehensive tool to create and run containers locally or on a single host. Kubernetes is suitable for operators who need a powerful and scalable tool to manage clusters of servers and containers across different environments. Podman is suitable for anyone who needs a secure and lightweight tool to run containers individually or in pods without a daemon. Benefits of using containers in the cloud. Developers use containers in the cloud because they offer many advantages over traditional methods of software development and delivery. Containers enable faster innovation, lower costs, and higher quality. Containers are compatible with the principles of DevOps. DevOps is a culture and practice of collaboration between developers and operations teams. DevOps aims to deliver software products faster and more reliably than traditional development methods by using automation, continuous integration, and continuous delivery. Containers make it easier to test, deploy, and update applications in the cloud. There are 3 key benefits of using container applications. They can run on any cloud platform that supports them, without requiring changes to the application code. This means that developers can focus on creating and updating their applications, without worrying about the underlying infrastructure or compatibility issues. Because users can create and destroy containers in seconds, containers also facilitate faster deployment and easier updates. Developers can group them together into clusters. Clusters are collections of containers that work together to provide a service or function. For example, a cluster of containers can run a web server, a database, and a load balancer. Developers can use tools such as Kubernetes to manage their clusters. About this module. Module 3. Microservices. Introduction. In this module, you'll learn about microservices. You'll discover how they work and identify the benefits of modular software. You'll review a scenario of a company implementing microservices on the cloud and then learn about the additional benefits of using containers to deploy microservices. You'll also explore how microservices communicate with each other. Learning objectives. After completing this module, you should be able to describe the purpose and benefits of microservices. Explain the process of developing, deploying, and managing microservices. Describe the process of using containers to deploy microservices. Describe the benefits of microservices communicating through application programming interfaces, APIs. Software goes modular. In traditional computing, everything a software package needs to perform its tasks is included in the software itself or be part of the operating system. Suppose you install an image editing application which includes a feature for adding in images from an online image library. You must write the code to perform that function into the application. Functions that perform a specific task are also called services, and a typical software application consists of several services bundled together. Breaking software into pieces. An application icon in the center with 8 circles around it representing different services. As building software developed, engineers began packaging services that many applications could use into libraries. A library is a collection of software functions that do certain things. For example, all the applications in an Office suite might share services like file management, spell and grammar checker, font management, and some layout features. Engineers package services like these in a library that all the applications would share. Each application makes a call to the library to run the code for the service they need and get back a result or some data. Bundling standard chunks of code, or services, into a library enables many applications to share the same code. This reduces the amount of code that applications need to contain and that computers need to store. It also helps users become familiar with standard functionality. For example, Using a standard open file dialog box across applications creates consistency and reduces the learning curve for users. And it ensures that when a developer updates the code, all applications can easily use the new functionality without needing to distribute a new version of the application. This was the first step towards modularizing software. Modular software and the cloud. If you've ever been to a mall, you know that the shops in the mall work together to provide a seamless shopping experience for all their customers. But each shop in the mall operates independently and specializes in a particular product or service. The idea of dividing software up into independent services is applied to cloud software in the form of microservices. Microservices are a way of designing cloud-based applications to consist of many small, independent, and loosely coupled services. Loosely coupled means that the services are connected to each other and each service performs a specific function by communicating with other services. Microservices communicate using application programming interfaces, APIs. An API defines how a microservice can communicate with other microservices or applications. It specifies the functionality that the microservice offers, the information the microservice needs to perform each piece of functionality, and the format that the information should be supplied in. The format that the microservice will use to pass any information to the other microservice. Microservices offer benefits to developers. They enable faster development, easier deployment, and more flexible scaling of cloud applications. They allow developers to use different technologies and languages for different services, depending on their needs and preferences. They help deliver agile and resilient software for the cloud. Microservices in practice. How would a company use microservices in developing and deploying an application on the cloud? Explore the following scenario to learn more about a real-world application of microservices. Company: Simply Home is an online retailer selling various products to customers around the world. Goal: it wants to improve its customer experience, scalability, and agility by adopting a microservices architecture for the software that runs its online catalog. Requirement: each microservice will be responsible for a specific business function or domain. For example, the product catalog, the shopping cart, order processing, payment, inventory, and shipping. Approach: Simply Home decides to use cloud computing to host and run its microservices. Remember, cloud computing is the delivery of computing resources such as servers, storage, databases, networks, and software over the Internet, on demand. Cloud provider: Simply Home decides to choose a cloud provider that supports microservices development and deployment, such as IBM Cloud, Amazon Web Services, AWS, Microsoft Azure, or Google Cloud Platform. Let's learn about how Simply Home does this. Register the microservices. Simply Home uses a microservices catalog to keep track of what each microservice is, how it operates, and how to access it. Route the requests. Simply Home uses the cloud provider tool to make sure requests from client applications go to the right microservice. It also allows the company to keep everything secure and running smoothly. Communicate between microservices. To enable communication between microservices, Simply Home uses the messaging system provided by the cloud provider. This allows the microservices to communicate with each other, even when they're busy responding to requests from other microservices. Store settings. The company uses the cloud provider storage to store all the settings for its microservices. This enables the company to easily update the settings when needed. Avoid errors. The company uses the cloud provider tool to prevent problems from spreading between microservices if one of them stops working. Integrate and deploy microservices. Simply Home uses Docker or Kubernetes to package and run its microservices. This ensures that the microservices are fast and don't interfere with each other. Test microservices. The company uses Jenkins or GitLab to automatically test and update its microservices. This ensures that everything is working well and the microservices stay up to date. Monitor microservices. The company uses the cloud provider tool to monitor how the microservices are working. This enables them to fix problems quickly if anything goes wrong. By using microservices and cloud computing, Simply Home can achieve a software solution that is modular, scalable, resilient, secure, and easy to update and maintain. They can also deliver their products faster and provide better value to their customers, giving them a competitive edge in the market. Using containers to deploy microservices. One of the challenges of developing and maintaining microservices is ensuring that they can run reliably and consistently across different environments. Developers can use containers to deploy microservices in a consistent and reliable way. By using containers to deploy microservices, developers can avoid the problems of incompatible software versions, conflicting dependencies, and varying operating systems that can cause errors and inconsistencies. Introduction. Explore the following steps from the point of view of a developer to learn about the steps to package and deploy a microservice using a container. Step 1. Write the code. Icon representing code. First, the developer writes the code for the microservice using the programming language and framework of their choice. Step 2. Create the container image. Icon representing containers. The developer uses a tool like Docker to create a container image for a microservice. A container image is like a recipe that tells the computer how to build and run the container. The developer includes information such as the base image, the code files, and the commands to execute when the container starts. This makes it easy to create and run containers consistently. Step 3. Test the container image. Icon representing DevOps. The developer tests the container image locally using a tool such as Docker Compose. This tool allows the developer to run multiple containers together and simulate how they interact with each other and with external services. The developer checks whether the microservice works as expected and meets the functional and non-functional requirements. Step 4. Publish the container. Icon representing container publishing. The developer pushes the container image to a registry, such as Docker Hub or Azure Container Registry. A registry is a centralized repository that stores and distributes container images. The developer can tag the image with a version number or a descriptive name to identify it easily. Step 5. Deploy the container. Icon representing container deployment. The developer sends the container image to a target environment like a cloud platform or an on-premises server using a tool like Kubernetes or Docker Swarm. These tools help manage containers across multiple machines. They also provide features like load balancing, health monitoring, and scaling. The developer can set up the deployment using files that specify how many copies of the container to run and what resources to allocate. By following this process, the developer can package and deploy a microservice using a container in a consistent and reliable way. This can improve the quality, performance, and availability of the microservice and reduce the complexity and cost of development and maintenance. How microservices communicate. An application programming interface, API, is a set of definitions and protocols that enable two software components to communicate with each other. For example, here's an illustration that shows how a weather app on someone's phone can use an API to request weather data from a server that hosts a weather database. The server responds with the data in a defined format, such as JSON or XML. APIs are like contracts that define how microservices can exchange information and request services from each other. They specify what sort of data can be sent and received, how to format the data, and what rules and protocols to follow. APIs enable microservices to work together as a cohesive system, while maintaining their autonomy and scalability. Remember the scenario of the Simply Home online shopping application that uses microservices for different tasks, such as the product catalog, shopping cart, payment processing, and order fulfillment. Each microservice has its own API that defines how it can interact with other microservices. Let's learn about how microservices use APIs to communicate with each other. Browse the catalog. When a customer browses the product catalog, the catalog microservice sends a request to the shopping cart microservice through its API. The catalog microservice asks for the items and quantities in the customer's cart. Send catalog items. The shopping cart microservice responds with the relevant data through its API. Place an order. When the customer places an order, the payment microservice sends a request to the order fulfillment microservice through its API, asking for the shipping details and confirmation. Fulfill the order. The order fulfillment microservice responds with the tracking number and status through its API. By using APIs to communicate, microservices can achieve several benefits. Modularity: developers can develop, test, deploy, and update each microservice independently, without affecting other microservices. Reusability: different applications and systems can reuse each microservice. Scalability: developers can scale each microservice up or down according to the demand and load, without impacting other microservices. Reliability: each microservice can handle errors and failures gracefully, without causing the whole system to crash. Flexibility: each microservice can use different technologies and frameworks that suit its needs, without being constrained by the choices of other microservice developers. About this module. Module 4. APIs. Introduction. In this module, you'll learn about application programming interfaces, APIs, which developers use widely on the cloud. You'll learn about the benefits that APIs provide to developers and the ways cloud computing makes use of them. You'll also explore the process of automating cloud tasks by using APIs. Learning objectives. After completing this module, you should be able to describe the function of APIs. Identify the role that APIs play in cloud computing. Identify 3 types of APIs that developers use in cloud computing. Explain the benefits of automating tasks using APIs. Data in, data out. Application programming interfaces, APIs, have been a part of computer programming since the earliest days of computer science. In their simplest form, an API is a means by which computer programs and services can send data and receive data from each other. More precisely, an API is a set of rules and instructions that allow different software applications to communicate and exchange data with each other. You can think of an API as a translator or a messenger that helps 2 parties understand each other and get what they want. For example, when you use a travel website to book a flight, the website uses an API to send your request to the airline system and get back the available options and prices. The API acts as a bridge between the website and the airline, making the process faster and easier for both sides. Call me. When one application requests data from an API, the application is making a call to the API. When the other application responds with data, the API is sending a response. Applications can make different types of calls to APIs. Select each number in order on the following diagram to learn about how applications communicate with each other using an API. The API for the software on the server defines how the client should interact with the server application and in what format the server can send or receive data. The client can verify the structure of the API before it sends a request by using special documents. The client application structures the call to the server API so it can send or receive data properly and securely. When the server application gets the request from the client, it looks at the call and constructs a response according to the structure of the call. The server sends the response back to the client with a status message and any requested data. APIs in cloud computing. APIs play a vital role in cloud computing. They enable the development, integration, and management of cloud-based applications and services. APIs allow developers to access and use the functionality and resources provided by cloud service providers, such as Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform. APIs also allow users to connect multiple cloud services or platforms, or to connect cloud and on-premises applications. For example, an online retailer might use APIs to integrate its website with a cloud-based payment system, a cloud-based inventory management system, and a cloud-based shipping service. There are three key types of APIs that developers can use in cloud computing, each providing different levels and types of functionality and resources. Service APIs provide access to specific cloud services, such as storage, messaging, and analytics. For example, the AWS S3 API allows users to store and retrieve objects in the AWS S3 cloud storage service. Application APIs provide access to specific cloud applications, such as email, calendar, and social media. For example, the Gmail API allows users to send and receive emails using the Gmail Cloud application. Infrastructure APIs provide access to low-level cloud infrastructure components, such as virtual machines, containers, and networks. For example, the AWS EC2 API allows users to launch and manage virtual servers in the AWS EC2 cloud computing service. In summary, APIs are essential for cloud computing. They enable communication and data transfer between different software applications and services in the cloud or between the cloud and on-premises servers. APIs also facilitate the development, integration, and management of cloud-based solutions. APIs allow businesses to customize and optimize their cloud solutions according to their specific needs and preferences. They can choose which features and functions to use or ignore from the cloud provider's offerings. APIs also enhance the security and reliability of cloud solutions. This is because they can use encryption, authentication, and error handling mechanisms to ensure data integrity and availability. Automating cloud tasks using APIs. By using APIs, a developer can write scripts or programs to interact with cloud services and perform tasks automatically, without requiring any human intervention. APIs enable developers to automate cloud tasks in a faster, easier, and more efficient way. This is because they can use existing code libraries and frameworks that support various API standards and formats. API automation in business. Review the following example to learn how a company uses APIs to automate the cloud services they use to run their business. Skillstream sells online courses and wants to streamline its operations and reduce costs by using cloud services. Skillstream has a website that allows customers to browse and purchase courses, a database that stores customer information and course content, and a learning management system, LMS, that delivers the courses and tracks the progress of learners. They decide to use APIs to automate tasks on the cloud, such as creating and updating user accounts in the LMS using the customer information from the database, uploading and updating course content in the LMS using the files from the database, sending email notifications to customers when they purchase a course, complete a module, or receive a certificate by using an email service provider. Generating and downloading reports about sales, revenue, and learner performance using a data analytics service. Skillstream uses different cloud providers for each of these services and integrates them using APIs. By using APIs, the company can automate tasks on the cloud without having to write complex code or manage servers. This saves time, money, and resources for the company, and improves the customer experience and satisfaction. Reflection: what do you think? What's one way you can think of that this business can use APIs to automate work using cloud services? Evaluate your thinking. Does your answer account for the following? Database backup. Using APIs for maintenance and servicing the database can save a lot of manual work. For example, systems that service many learners generate a lot of progress data that the company wouldn't want to lose. They could use an API to perform nightly backups of that data. Easier registration. APIs can automate and facilitate time-intensive tasks like learner registration. For example, many learners have a social media account or are registered with a college or university. The company could use APIs to communicate with those social media companies or educational institutions to access user data, making it easier for learners to register for an account on the LMS. How API automation works. In the example above, Skillstream uses API automation to send email notifications to their learners. The learner initiates the process by performing a task such as purchasing a course or completing a course to receive a certificate. The completion of the task initiates an event in the LMS. An event is a change in the computer system that an automated process can use to start a chain of actions. Introduction. Explore how Skillstream uses cloud APIs to automate the process of sending emails to learners. Note, typically, companies work with an email service provider, ESP, that provides APIs for sending emails. The ESP provides the company with everything they need to automate emails. Step 1. Configure the email service provider API. Skillstream configures the ESP API for their LMS application. This involves setting up security measures and other settings required for the LMS application to communicate with the ESP API. Step 2. Integrate the API into the application. Next, the company integrates the ESP API into the application. Developers write code to send requests that tell the ESP API to send email notifications to learners. They can use a software development kit, SDK, that the ESP provides to make it easier to integrate the API into the LMS application. Step 3. Set up email templates. Before sending email notifications to learners, Skillstream creates email templates for each type of notification. These might include a purchase confirmation, module completion, or certificate receipt. Step 4. Trigger emails. Once the company has set up the email templates, they can trigger the email notifications to customers using the ESP API. They trigger email notifications based on events in the LMS, such as when a learner purchases a course, completes a module, or receives a certificate. Step 5. Monitor email delivery and analytics. It's important to monitor email delivery and analytics to ensure that the email notifications are reaching learners and are effective. The ESP API provides analytics data such as open rates, click-through rates, and bounce rates, which the company uses to optimize their email notifications. Summary. Skillstream uses cloud APIs to send email notifications to learners by working with their email service provider to configure their API, integrate the API into their application, set up email templates, trigger emails, monitor email delivery and analytics. Integrating services using APIs enables businesses to automate tasks on the cloud without having to write complex code or manage their own on-premises servers. This reduces the time it takes to deliver services to their customers and the ongoing costs of maintaining their applications. About this module. Module 5. Use cases and best practices. Introduction. In this module, you'll learn about 2 use cases for containers, microservices, and APIs. You'll discover how to use them to migrate legacy apps to the cloud and build scalable applications. You'll also identify some best practices for using containers and microservices. Learning objectives. After completing this module, you should be able to describe the process of using containers, microservices, and APIs to migrate legacy apps to the cloud. Describe the process of using containers, microservices, and APIs to build scalable applications. List the best practices to use when working with containers and microservices. Using containers, microservices, and APIs to migrate legacy apps to the cloud. 3 rows of 3 shapes signifying progress. The shapes are a circle, a triangle, and a square. The top row shows only half of each shape, the second row shows more of the shape, and the final row shows the whole shape. Many companies have old computer programs that are difficult to update and keep running. These programs often use outdated technology and are built in ways that make them hard to change. To make these programs work better and take advantage of new technology like cloud computing, companies can use tools like containers, microservices, and APIs. Containers help separate the program from the computer it runs on and include all the resources and configuration settings that software needs to run independently. Microservices divide programs into small parts that can work together. and APIs help these parts talk to each other and to other programs. By using these tools, companies can migrate, or move, their old programs to the cloud to make them easier to manage and improve how they work. Containers, microservices, and APIs in practice. The thought of moving from existing apps to the cloud can be daunting. Disrupting a running business, even for a short time, can have a negative impact. However, using containers, microservices, and APIs to modernize a business's applications can far outweigh the short-term impact the disruption might cause. Explore the following scenario to learn about how developers use containers, microservices, and APIs together to provide benefits for a business that wants to migrate to the cloud. ABC Incorporated is a large enterprise that provides software solutions to various industries. The company has a portfolio of legacy applications that their developers have created over the years using different technologies and platforms. These applications are critical for the business operations and customer satisfaction, but they also pose several challenges for the company. They are difficult to maintain and update due to their traditional architecture and complex dependencies. They are costly to run and scale due to their high resource consumption and low utilization. They are vulnerable to security breaches and performance issues due to their outdated code and infrastructure. Introduction. To address the challenges, ABC Incorporated decides to migrate their legacy applications to the cloud using a modern approach based on containers, microservices, and APIs. Step 1. Analyze. They analyze their existing applications and identify the core functionalities that they can break down into smaller, independent components and reuse across different applications. Step 2. Design and develop. They design and develop microservices that match these functionalities and components. Each microservice has a clear way of communicating with other microservices by using APIs. Step 3. Package. They package each microservice into a container image that contains all the dependencies and configuration the microservice needs to run independently. They use a container registry to store and manage these container images. Step 4. Deploy. They deploy each container image to a cloud platform that provides management and monitoring tools. The cloud platform also has a tool, called a service mesh, that connects and manages the communication between the microservices. Step 5. Test. They test and validate the functionality and performance of the migrated applications using automated tools and processes. They also implement continuous integration and delivery pipelines to enable faster and more reliable updates. Step 6. Monitor. They use logging and monitoring tools to help them detect and troubleshoot errors and performance problems. By continually monitoring the deployment, they have ongoing insights into the behavior and health of the system. ABC Incorporated has successfully migrated their traditional application to a microservices architecture. By migrating its traditional applications to the cloud with containers, microservices, and APIs, ABC Incorporated achieves several benefits. They reduce the complexity and cost of maintaining and updating their applications by breaking them down into smaller and simpler units that they can independently develop, deploy, and manage. They increase the efficiency and scalability of their applications by leveraging the elasticity and automation of the cloud platform and the lightweight nature of the containers. They improve the security and reliability of their applications by applying best practices to their code and infrastructure. ABC Incorporated is now able to deliver more value to its customers and stakeholders by offering more innovative and responsive software solutions that meet their evolving needs and expectations. Using containers, microservices, and APIs to build scalable applications. Business people sitting around a table with laptops and devices during a meeting at work. In today's fast-paced and competitive market, businesses need to deliver high-quality software products and services faster and more efficiently than ever before. To achieve this goal, many businesses adopt a modern approach to software development that leverages containers, microservices, and APIs. These technologies enable businesses to build scalable applications that can run on any platform, Adapt to changing customer needs and preferences. Integrate with other systems and services easily and securely. Combining containers, microservices, and APIs provides fulfillment, modularity, and availability. Fulfillment. Containers provide a lightweight and portable way to package and deploy applications, making it easy to scale applications up or down based on demand. This allows companies to quickly respond to changing business needs and user demands, while also ensuring efficient use of resources. Modularity. Microservices divide an application into smaller, independent components that developers can create, deploy, and scale independently. This allows companies to scale specific parts of their application as needed, rather than having to scale the entire application. This can result in more efficient resource usage and faster response times. Availability. Using a container orchestration platform like Kubernetes can enhance scalability. Kubernetes provides powerful tools for managing and scaling containerized applications, allowing developers to easily scale their applications up or down based on demand. It also provides features like automatic failover and rolling updates, which help ensure that applications are always available and up to date. By using containers, microservices, and APIs, developers can create scalable applications that can handle high demand and complexity with greater efficiency, agility, and reliability. A case study. You can better understand how a microservices architecture can accelerate a business by exploring how IBM worked with an airline company to implement a microservices architecture to improve its customer experience. Examine the following cards to learn about this implementation and how IBM used the power of microservices to enhance a business's customer experience. Select each card to follow the case study. Simplify the customer experience. The airline wanted to simplify the customer experience while providing more choices. The airline planned to create a new platform for all their digital services. They adopted a microservices architecture on an open, highly scalable hybrid cloud platform. This gave the airline reusable components to accelerate their delivery of new applications. Deploy to the cloud. IBM successfully moved the application to Kubernetes to create a solution and deployed it on the IBM Cloud Kubernetes service. Because the airline was using containers, they were able to easily deploy the containers in different cloud environments and locations to be compliant with local data protection regulations. Experience results. Because the airline was able to break down the application into small, independent services that they could easily reuse and scale as needed, development was significantly faster. Using a microservices architecture approach, the airline was able to deliver a new web check-in application in just 15 weeks. They had originally anticipated a delivery time of 9 months. Source: Delivering a Premium Travel Experience, opens in a new tab, IBM, by Leah Valentine. Best Practices when Using Containers and Microservices. Deploying microservices using containers can offer many benefits, such as scalability, portability, resilience, and faster development cycles. However, it also introduces some challenges, such as managing the complexity, security, and performance of the distributed system. Therefore, it's important to follow some best practices when deploying a microservices architecture using containers. Here are some best practices. Design each microservice to be loosely coupled and highly cohesive. This means that each microservice should have a clear and single responsibility, and should minimize its dependencies on other services. This way, businesses can develop, test, deploy, and update each microservice independently, without affecting the rest of the system. Use a consistent and standardized approach to communicate between microservices. Businesses can do this by using common protocols, formats, and patterns for inter-service communication, such as RESTful APIs, JSON, and message queues. This can help to ensure interoperability, reliability, and security of the communication. Implement proper logging, monitoring, and tracing mechanisms for each microservice and the whole system. This can help to detect and troubleshoot errors, performance issues, and anomalies in the system. It can also provide useful insights into the behavior and health of the system. Use a container orchestration tool to automate and manage the deployment, scaling, networking, and configuration of the containers. This can help to simplify the complexity of managing many containers across different environments. Some of the popular container orchestration tools are Kubernetes, Docker Swarm, and Amazon ECS. Apply security best practices at every level of the system. This includes securing the communication between microservices using encryption and authentication. It also includes securing the containers using techniques such as scanning for vulnerabilities, limiting privileges, and enforcing policies. About this module. Module 6. You're a cloud engineer. Introduction. In this module, you'll learn about your new cloud engineer role. You'll be working alongside a senior engineer who is an expert in cloud computing. They will guide you through the process of creating a Docker container, and then running and testing the web app in the container. Learning objectives. After completing this module, you should be able to identify typical tools and skills to apply when working with applications using containers. Create a Docker container. Install an app into a Docker container. Review and test the running app in the container. Your new cloud engineer role. It's your turn. A cloud engineer's ID badge. You've done it. You've studied, practiced, and worked alongside other professionals. Now you have accepted a role as a cloud engineer. It's your turn. What does your new job involve? Assignment. Your first task is to assist a senior cloud deployment engineer to create a Docker container and install an existing web app to the container. Select each card to learn more. Your role. Your entry-level role is to provide general support for other cloud engineers to build your global company resources on the cloud. Your customers. Your department focuses on creating and delivering internal company software and services using the cloud. Your area. You work alongside deployment and database experts to assist them in their work. The toolkit. As a cloud engineer, you will use a variety of tools depending on the task. You'll use the interface from your company's cloud provider to interact with their cloud services. And you'll also use code editors, database tools, and other third-party tools to create software services for the cloud. Woman typing on a laptop in an office. You have a set of tools to use on this project. The tools you'll use are Docker, the Node.js framework, and the code editor Visual Studio Code. Take a moment to learn about each tool. Docker, opens in a new tab, is a software platform that enables you to build, run, and share applications using containers. Docker provides tools and services to create, manage, and orchestrate containers. You can also use it to store and distribute software platforms to build, run, and share applications using containers. It's free for personal use. Node.js, opens in a new tab, is a tool that enables you to run JavaScript code outside of a web browser. It's useful for building web applications that need to handle a lot of data or real-time events. You can use Node.js to create servers, APIs, chat apps, and more. It also has a large library of modules and packages containing pre-written code that you can use in your applications. Node.js is open source and free to use. Visual Studio Code, opens in a new tab, is a code editor for building and debugging web and cloud applications. Also known as VS Code, it's a Microsoft product for Windows, Linux, and Mac OS operating systems. It's free and you can access it to try it out yourself. The skills to apply. As a cloud engineer, you are going to learn the skills to build and fill a container. You'll apply technical and testing skills to be successful in your job. Technical skills. Read and write code at a fundamental level to create basic Docker instructions. Run instructions from a command line interface, CLI. Testing skills. Ensure the container is built properly by viewing the container in a desktop tool. Run the container to ensure it loads properly. View the application in the browser that is running in the container. Cloud engineers use a variety of these skills when working with cloud services. In the building a Docker container scenario in this course, you'll practice using code to configure and build a Docker container, and use command line instructions to install an app into the container. Your first project. Purpose of the project. The software development team in your company developed a small web application to help employees manage their tasks. Your team will deploy this application to locations all over the world to improve how well people organize and manage their work time. Your scope of work. The development of the web application is complete. Your team is ready to create a container for it. The senior cloud engineer decides to install the app into a Docker container to make deployment and maintenance easier. They've asked you to help on the project by assisting them to create the container and install the app image into it. The container will work as follows. During the build process, the container includes all the files it needs to run a Node.js web server. The container also includes 3 application files, script.js, style.css, and index.html. Once you create the image and place it in the container, you'll start the container and Docker will launch the Node.js web server which will serve the web application. Working together. In this simulation, you'll be pair programming with the senior engineer on their laptop. Pair programming is a software development technique in which 2 programmers work together on one computer. One of them, called the driver, writes code. The other one, called the observer or navigator, reviews each line of code, and gives feedback. The 2 programmers frequently switch roles to share their skills and perspectives. During the simulation, you will take the role of the observer when reviewing the work of the senior engineer and the role of driver when writing code. Important note, you do not need to install, download, or run files to complete this course. You'll use the following simulation to practice the steps and learn in a safe, pretend environment. Let's get started. Simulation, create a Docker container and install an app. Clara, the senior engineer, already has installed Docker, VS Code, and Node.js on her laptop. She has created a folder and copied the 3 app files into it. In this simulation, you will follow the steps to create a Docker container, install an app into that container, and test the running app. There are 15 steps to complete. Note, be sure you carefully type the code exactly as it displays, and check your work. Avoid extra spaces, and don't forget semicolons. This is a key skill to build as a cloud engineer. Simulation transcript. Create a Docker container and install an app. Clara, the senior engineer, welcomes you to the project. You've got VS Code open and you're ready to start. Clara points out the areas you'll be using. Notice the following 3 sections. And hover over the icons. Then, select the next arrow to continue. Clara explains that the first step is to create a file called a package.json. This file holds the information that Docker uses to create and run the web server. Clara creates the file and writes the first few lines of code. Take a moment to review the code that sets up the app name, version, and more. Select the next arrow to continue. The code pad provides all the code you need to complete your coding work. You will refer to it throughout these steps. Select each field under Clara's code and then type each line of code exactly as you see it in the code pad. For example, in the field at line 7, you would type scripts : It's time to try it out. Select the next arrow to continue. You'll complete the package.json file by writing the instructions that tell Node to start the web server. Below the last line in the package.json file, type the following code. Type 1 line of code in each field exactly as it displays in the code pad. Select each field to start typing a line. When you finish typing all of the code, press Enter. CodePad code. Scripts. Start, Node server.js. Dependencies. Express, 4.16.1. 4 Clara compliments you on your work. Well done. The senior engineer explains that the next step is to create a server.js file. This is a script that Node.js uses to provide instructions for how the web server will operate. Clara creates the file and writes the first few lines of code. Take a moment to review her code. Select the next arrow to continue. 5 Clara asks you to complete this file by writing code to open communication between the browser and the web server using the settings she specified in her earlier code. Below the last line of code in the server.js file, type the following code. Then, press enter. Codepad code. App listen, port, host, equals. Console.log, running on http://$host:\port. 6 The final file you'll need to create is the Docker file. This is the specific file used by Docker that tells it which software and dependencies to use in the container. Select the next arrow to continue. 7 Clara creates the empty Docker file and asks you to write the instructions. Notice the commands include the run command to install npm into the image and the copy command to copy all the files. Finally, the cmd command runs the node.js file you previously wrote, which tells Docker to start the web server. Select the first line in the file and type the following instructions. Then, press enter. Codepad code. From Node 18 Alpine. Workdir/app. Copy package star.json/ run npm install. Copy. Expose 8080. cmd node, server.js. 8 Clara creates a file to tell Docker to ignore all the existing node.js files in the laptops folder because the instructions you wrote tell Docker to install them. Without this file, the Docker image might include unnecessary files in the image, increasing its size. Select the next arrow to continue. 9 Now you're ready to build the container. Clara explains that you'll be doing this in a terminal window using the command line. Visual Studio Code has a terminal built into it. Clara opens this window so you can write the command to build the container. Select the next arrow to continue. 10 Clara tells you to use Docker's build command to install the to-do app and build the container. Select the first line in the file and type the following instructions. Then, press enter. Codepad code. Docker build. Todo app. 11 Clara asks you to notice that the terminal window confirms that the container has been built successfully. Nice work. Now that the container is built, you're ready to test it. Clara explains that you'll run a Docker command to launch the container and load the image which contains the web app. Select the next arrow to continue. 12 To run the Docker container, place your cursor in the terminal window prompt and type the following command. Then, press enter. Codepad. Docker run p8080 todo app. 13 To verify the app is running, Clara opens the Docker app and highlights the running container with the to-do app image loaded. Now you can browse to the website that is running inside the container using Node.js to deliver the web pages. Select the next arrow to continue. 14 Because it's a web app, you can test the application using a browser. The Docker app provides a link you can use to browse to the site. When you select the link, the to-do app opens in the browser. Select the highlighted active port number for the running container that has the web app running inside it. 15 Clara congratulates you on a successful build. Notice that the Node.js application launches when you run the image through the Docker engine. This means you correctly packaged the Docker image and the container is ready to be deployed to the cloud so employees all over the world can use it. Select the next arrow to continue. You successfully packaged a web application into a container image, created a Docker container and loaded the image into it, and ran the application inside the container. You also tested the application to ensure it ran from the container as expected. Great work! You successfully partnered with the senior cloud engineer to deploy a web application for your company's employees all over the world to manage their tasks. Explore more. Check out these resources if you'd like to explore the tools simulated in the scenario. Opens in a new tab, Node.js, opens in a new tab, to download and install Node.js. Node.js Guides, opens in a new tab, to learn more about using Node.js. Docker, opens in a new tab, to download and install the Docker application. Docker Get Started Guide, opens in a new tab, for step-by-step instructions on how to get started with Docker. Visual Studio Code, opens in a new tab, to download and install Visual Studio Code. Learn to code with Visual Studio Code, opens in a new tab, to learn more about using Visual Studio Code. You've come so far and learned so much. You learned about virtualization and the benefits it provides in the cloud. You explored different virtualization technologies and when to use them. You discovered the advantages that microservices offer to a cloud application and how they use APIs to communicate. In the last module, you practiced what you learned by using a simulation to create a container and run a web app in it. Now that you've completed this course, you should be able to explain the purpose and benefits of virtual resources. Describe the purpose and function of using containers in the cloud. Describe the purpose and function of using microservices in the cloud. Identify key features of application programming interfaces, APIs. Recognize use cases and best practices for virtualization in cloud computing. Create, install an application, and test a Docker container. Key points to remember. 1. Virtualization is the process of creating a virtual representation of a physical resource. 2. A virtual machine, VM, is a software-based emulation of a physical computer that can run different operating systems and applications. They can reduce hardware costs, power consumption, and space requirements. Improve server utilization and performance. Provide high availability and fault tolerance. Enhance system security. 3. Virtual storage is the pooling of physical storage from multiple network devices into what appears to the user as a single storage device. It can reduce the storage needed on internet-connected devices. Enable data access from anywhere. Allow users to scale their storage up or down depending on their needs. 4. A virtual network is a network built from virtual components instead of physical hardware. It can enable users to create isolated environments for development and testing. Connect different physical locations or cloud services together. Enhance the performance or availability of network services. 5. Containers are a lightweight form of virtualization that enables applications to run in isolated environments that share the same operating system and hardware as the host server. 6. Containers are easy to deploy, replicate, and update across multiple host computers. 7. Using a container orchestration tool to automate and manage the deployment, scaling, networking, and configuration of the containers can simplify the complexity of managing containers across different environments. 8. Microservices are a way of designing cloud-based applications to consist of many small, independent, and loosely coupled services. They enable faster development, easier deployment, and more flexible scaling of cloud applications. They are more scalable and resilient than traditional applications. 9. Microservices can use any programming language or technology and they communicate by using APIs. 10. Developers use containers to simplify the deployment and maintenance of microservices. 11. An API is a set of rules and instructions that allow different software applications to communicate and exchange data with each other. They allow developers to access and use the functionality and resources provided by cloud service providers. Automate cloud tasks in a faster, easier, and more efficient way. 12. Containers, microservices, and APIs work well together to migrate legacy apps to the cloud and to build scalable applications.